Okay then guys, let's have a little look at ellipses then, a little intro into this. What is an ellipse? Well, generally it's a set of points that is generated by maintaining a constant ratio between a point and a fixed line. The ratio is less than 1, namely that the distance between the point and the straight line is the longer of the distances. So we call that ratio E, so E times this distance will equal this distance. When we impose that condition, we'll generate what is termed an ellipse. So let's have a look how that pans out in practice then. For convenience, we take AE as the focus, so there's our focus point, here's our directrix line, and we take the line x equals a over e as the directrix, as is customary. Let's see how that pans out to an equation then. So let's have a look at this. So here's the x-axis, we put AE naught, the focus point here. Here's our directrix, and here's our set of points P that we're going to generate now. The ratio of this distance, which we've labelled D, is E times this distance is equal to the smaller distance, because E is less than 1, isn't it? If you forget. So that would mean then that the square of this, ED squared, is equal to this distance, isn't it? Squared. So ED squared is equal to this distance squared, which is a triangle. X minus AE is the difference between the x points, and the height of this triangle is y. So square both using Pythag and we get this distance squared. The ED squared that we mentioned before, well, D is none other than just the difference between the x values. X minus A over E, so put that in here. So, and we can say that's E squared times D squared, as we've said. So we've got this thing here. Let's expand this bracket then. So this is going to be x squared times the E squared. Then we'll have minus 2ax over E times an E squared. So the E underneath will cancel and we'll be left with 1 over on top with a minus 2ax as well. Then if we square this, we'll get a squared over E squared with a plus. And the E squareds will cancel to leave a squared. This is just x squared, minus 2aex goes there, and then plus a squared e squared when we square this, don't we? Minus times minus is a plus our y squared. You'll notice that the minus 2aex is cancelled here and here. The x squared, well, let's bring this thing here over to there, and we're writing on the right from right to left. So that'll be one of these, minus e squared, lots of x squared, so that's those two taken care of. We've got the y squareds, as is, so that's that done. Then we've got an a squared left here, which now is over here, and then we're going to move this to minus a squared e squared, and we can put it in a bracket, minus a squared e squared in a bracket, so this is what we get. Now let's divide by 1 minus e squared times a squared. Divide by this all the way through, so that will leave 1 here. Then we'll divide by this under the y squareds, of course, and divide by this under the x squareds. The 1 minus e squareds cancel, and we're just left with a squared. So we get this equation now. If we just let b squared, instead of writing all this bump, we can just let another variable, b squared equal a squared times this 1 minus e squared, and then we come down to this classical form of the ellipse. This is how we generally write an ellipse in a user-friendly, easy to understand fashion. So there's our ellipse then. So let's have a look at how we would sketch that equation there. I've written it again in this section here. Here it is here. So how would we sketch it and find, say, tangents and perhaps even normals as well? Okay, well, this is what we've got. So if we just let y equal 0 then, this will be 0, and we'll get x squared, bring the a squared up, you'll get x squared equals a squared. So that tells us x equals plus or minus a. So you get this coordinate and this coordinate here. When x is 0, you put that in there, you'll get y squared over b squared is 1. So move the b squared up, y squared is b squared, square root both sides, y equals plus or minus b. So when x is 0, y is plus or minus b. Now, what happens here? Well, if you rearrange it in another way, move this over the other side, 1 minus, and then move the a squared up after, and divide to times, we get this. Now here we can see that x squared is equal to this. So for x to have a value, this must be positive, mustn't it? For x to have any values. So this must be smaller than 1, or equal to 1. And if that holds, then you can move the b up, and you get y must be smaller than b, mustn't it, on either side. So for x to have values, y can only vary between these two values. And for looking at the other way round, let's rearrange it the other way round now. So move the x squared over a squared over, 1 minus, and then move the b squared from divide to times, so we get this. And then that tells us for y to have values, x can lie in the range where this is positive, and this is positive provided this holds, isn't it? This must be smaller than 1. And then you move the a squared up, and then you square root, and you can see that for this to hold, x has got to lie between a and minus a. So for y to have values, x has got to lie between a and minus a. And there's also symmetry we can observe as well on both the x-axis and the y-axis from these equations when we square root. We'll get plus and minuses, won't we, as solutions. So there's symmetry there. Let's differentiate implicitly now. 2x over a squared plus 2y over b squared multiplied by the something differentiated, which is dy dx, equals constant goes to 0. Rearrange, leave the dy dx where it is, as is. Move the 2x over a through the equals to minus 2x over a squared. And then once you've done that, in our mind's eye, we'll move the b squared from divide to times and the 2y from times down to divide. The 2's will cancel. We're just left with minus b squared x on top, a squared y underneath. And we can see from this gradient function here, when x is 0, dy dx is 0, so it flattens out here. And when y is 0 and x is non-zero, it's undefined, isn't it? Meaning it will shoot off to infinity. So that's why we've got vertical lines here. So that then enables us to be able to join all these points up here. And it's symmetric both through the x-axis and the y-axis here. So this is our ellipse in question. So good luck with this section then, guys. There's a lot to take in here, I know, but it's best explained by examples. So I hope you get something from the questions, and I'll catch you in the next section. Cheers!